What are the Xms and Xmx parameters when starting the JVM? Introduction. When running Java applications, especially backend systems like Spring Boot or microservices, memory tuning becomes important. The JVM provides options to control heap memory size, mainly Xms, Xmx. These are commonly seen in Kirk, production deployments, Docker containers, application servers, Tomcat, WebLogic, Spring Boot startup scripts, performance tuning. A common interview question is, what are Xms and Xmx in Java? This topic explains what heap memory is, what -xms means, what -xmx means, how JVM memory allocation works, performance impact, best practices, common mistakes. What is JVM heap memory? The JVM allocates memory into areas: heap, objects, stack, method calls, metaspace, class metadata. The heap is where all objects are stored. Example, user equals new user. This object lives in heap memory. What is XMS? Definition: initial heap memory size allocated by JVM at startup. Example, XMS 512M. Meaning, say JVM starts with 512 megabytes heap memory. What is -xmx? Maximum heap memory JVM is allowed to use. Example, XMX2G. Meaning, check, JVM can grow heap up to 2 gigabytes. Simple comparison parameter meaning, XMS initial memory, -xmx maximum memory. Example JVM startup, Java-XMS 512M -XMX2G. This means start with 512 MB, grow up to 2 GB. How JVM memory works: app starts, allocate XMS memory, monitor usage, increase heap if needed, up to XMX limit. Why these parameters matter? Without tuning, JVM may use too little memory or grow unpredictably. With tuning, stable performance, predictable memory usage, better scalability. Difference in behavior, small. XMS 128M, XMX 2G. Clack, slower startup growth. Clack, memory expands gradually. Equal -XMS and -XMX. XMS 2G, XMX 2G. Fixed heap size, no runtime resizing, better performance in servers. Why set -XMS equals -XMX in production systems? COP avoids memory resizing overhead. COP reduces GC fluctuations. COP improves stability. Real-world example: Spring Boot app. Java-XMS 1G, -XMX 2G, -jar app.jar. Used in CUC, microservices, CUC, cloud deployments. Memory pressure scenario: if heap is too small, out of memory error. If heap is too large, waste of resources, slower garbage collection. JVM memory growth behavior: start -XMS, heap grows, hits -XMX limit. GC triggered heavily, possible OOM, common values in production environment. XMS -XMX, small app 256M, 512M. Medium service 512M, 2G. Large system 2G, 8G+. How to check JVM memory runtime info: runtime.getRuntime.maxMemory. Heap size effects: check GC frequency, pause time, throughput. Large heap: check fewer GC cycles, longer pauses. Common mistakes: 1. Setting XMX too high, -XMX 32G, may cause X slow GC, X system pressure. 2. Ignoring XMs, too small initial heap, X slow startup performance. 3. Not aligning container limits, Docker mismatch. Container 2 gigabytes, check JVM uses 4 gigabytes. Docker example Java, -XMS 512M, -XMX 1G, -jar app jar. Must match container memory limits. Cloud best practice. Always tune JVM per environment. Monitor heap usage. Use APM tools. Modern JVM auto-tuning. New JVMs can adapt memory better, but XMS and Xmx still widely used. Still important for production tuning. Simple definitions. XMS. Initial heap size allocated when JVM starts. -XMX. Maximum heap size JVM can grow to. Final summary. -XMS and -XMX control JVM heap memory. Check MSS means starting memory. Check MXX means maximum memory limit. Example. Java -XMS 512M -XMX 2G myapp. Key idea. These parameters help control memory usage, performance, and stability of Java applications in production.